NASA's James Webb Space Telescope detected something impossible. Mysterious red objects scattered across images of the early universe have finally been identified. They're not galaxies. They're not black holes. They're single stars with masses reaching 1 million times the sun, wrapped in wispy envelopes of gas. And scientists had no idea stars like this could exist. Right now, astronomers at Harvard and Smithsonian have confirmed these objects, called little red dots, are the most massive stars ever theorized. Each one contains more mass than entire star clusters, and they existed when the universe was less than 1 billion years old. These stars are completely metal-free, formed from primordial hydrogen and helium with zero heavy elements, violating every stellar evolution model we've developed over the past century. The luminosity of a single little red dot equals 10 billion suns, yet it's concentrated in a star barely larger than our solar system. Spectroscopic analysis shows emission lines that don't match any known stellar population, with line widths indicating velocities exceeding 10,000 kilometers per second in the surrounding envelope. Dr. Devesh Nandal, astronomer at the Center for Astrophysics and lead author of the study, stated in January 2026, "Little red dots have been a point of contention since their discovery. But now, with new modeling, we know what's lurking in the center of these massive objects, and it's a single gigantic star in a wispy envelope. Even more disturbing, these monster stars are so unstable they can only survive for a few thousand years before collapsing directly into supermassive black holes without ever going supernova. Little red dots have broken every assumption we made about the maximum mass limit for stars. Here's what should concern you most. If stars this massive existed in the early universe, they could explain how supermassive black holes weighing billions of solar masses appeared less than 1 billion years after the Big Bang. Something that should have taken tens of billions of years happened in a cosmic eye blink. Think about it. Before we dive deeper into this cosmic revelation, if you want to stay updated on what could be the most important discovery about the formation of supermassive black holes ever made, don't forget to click the subscribe button and turn on notifications, because what we're about to reveal will completely change how you understand the birth of the universe's most extreme objects. And leave a comment telling us, do you think we'll find even more massive stars hiding in Webb's data? Let's talk about how this mystery began, because understanding the confusion makes the solution even more shocking. When the James Webb Space Telescope began its science operations in July 2022, one of its primary missions was to observe the most distant galaxies ever detected, galaxies from the first billion years after the Big Bang. Webb's infrared capabilities allow it to see objects that are completely invisible to previous telescopes like Hubble. Light from these extremely distant objects has been stretched by the expansion of the universe into infrared wavelengths. Hubble, designed primarily for visible and ultraviolet light, couldn't detect them clearly, but Webb can. And as Webb began surveying deep space, astronomers started noticing something strange in the images. Scattered among the expected galaxies were tiny red dots. Not large, extended galaxies, not bright quasars, just compact red points of light. At first, astronomers assumed these were simply very distant, very faint galaxies. But when spectroscopic follow-up observations were conducted, measurements that break down the light into its component wavelengths to determine composition, temperature, and distance, the results didn't make sense. The spectra showed characteristics that didn't match normal galaxies. They showed characteristics that didn't match active galactic nuclei powered by black holes. They showed characteristics that didn't match anything in the existing astronomical catalogs. The objects became known informally as little red dots, or LRDs, and they became one of the biggest mysteries in early universe astronomy. The first papers published about little red dots in 2023 and 2024 proposed multiple competing theories. Some astronomers argued they were obscured quasars, supermassive black holes surrounded by so much dust that only red light could escape. Others suggested they were compact galaxies undergoing intense starbursts. A third group proposed they might be intermediate mass black holes, a poorly understood class of objects between stellar mass and supermassive black holes. But every theory had problems. The spectra didn't quite fit. The luminosities were wrong. The sizes were inconsistent. Dr. Nandal's team at the Center for Astrophysics decided to approach the problem from a completely different angle. Instead of trying to fit little red dots into existing categories of astronomical objects, they asked, what if these are something entirely new? They started with the spectroscopic data, the detailed measurements of the light coming from these objects. The spectra showed extremely broad emission lines, much broader than what you'd see in a normal galaxy. Broad emission lines indicate material moving at very high velocities, typically thousands of kilometers per second. In quasars, broad emission lines come from gas orbiting close to a supermassive black hole, where gravitational forces accelerate the gas to extreme speeds. But the emission line patterns in little red dots didn't match quasar patterns exactly. The team also looked at the luminosity, the total energy output. Little red dots are extraordinarily bright, shining with the power of billions of suns. But their brightness varies in specific ways that don't match black hole accretion. Then came the breakthrough. The team constructed detailed theoretical models of extremely massive stars far beyond anything known to exist in the modern universe. Stars with masses not of tens or hundreds of solar masses, but hundreds of thousands to millions of solar masses. These are called supermassive stars, and they're fundamentally different from normal stars. Normal stars, even the most massive ones observed today, stars of 100 to 300 solar masses, are held together by a balance between gravity, trying to crush them inward, and radiation pressure from nuclear fusion pushing outward. This balance creates a stable structure that can last millions of years. But as you make stars more and more massive, something changes. At masses above roughly 10,000 solar masses, the star enters a regime where radiation pressure becomes so intense that it can barely hold itself together. The star becomes unstable, pulsating and shedding mass. At masses approaching 100,000 solar masses and above, the star enters an even more extreme regime. It becomes what's called a supermassive star, an object so massive and so luminous that its structure is dominated by relativistic effects. The star is essentially a gigantic nuclear reactor on the edge of catastrophic instability. Here's the physics problem. In the modern universe, stars like this can't form. The gas clouds that collapse to form stars always contain some fraction of heavy elements: carbon, oxygen, iron, left over from previous generations of stars. These heavy elements act as coolants, allowing the gas to radiate away energy and fragment into smaller clumps. The fragmentation produces many smaller stars instead of one giant star. But in the early universe, less than 1 billion years after the Big Bang, the situation was different. The gas was primordial, containing almost no heavy elements, just hydrogen and helium from the Big Bang. Without heavy elements to cool the gas, collapsing gas clouds couldn't fragment efficiently. Instead of producing clusters of small stars, they could potentially collapse into single, extraordinarily massive objects. This is the environment where supermassive stars could form. And Dr. Nandel's team realized that the properties of these theoretical supermassive stars matched the observations of little red dots almost perfectly. The luminosity matched. An object with 1 million solar masses powered by nuclear fusion would shine with the luminosity of roughly 10 billion suns, exactly what little red dots show. The spectrum matched. A supermassive star would be surrounded by a hot, diffuse envelope of gas, material being blown off the star's surface by the intense radiation pressure. This envelope would produce exactly the kind of broad emission lines observed in little red dot spectra. The color matched. Supermassive stars have effective surface temperatures of around 10,000 to 30,000 Kelvin, hot by normal standards, but cooler than the most massive stars in the modern universe. At the extreme redshifts where little red dots are observed, this temperature range produces objects that appear red in Webb's infrared filters. Everything fit. The team published their findings in January 2026, presenting the results at the 247th meeting of the American Astronomical Society in Phoenix, Arizona. The paper was met with a mixture of excitement and skepticism. Excitement because it finally provided a coherent explanation for one of Webb's biggest mysteries. Skepticism because the implications are profound and unsettling. If little red dots are really supermassive stars, it means the early universe was capable of producing objects that dwarf anything we see today. But here's where it gets really strange. Supermassive stars are fundamentally unstable. The radiation pressure trying to blow them apart is almost equal to the gravitational pressure holding them together. They can only exist for a few thousand years, maybe 10,000 years at most, before catastrophic instability sets in. And here's the critical part. When a supermassive star dies, it doesn't explode as a supernova. It collapses directly into a black hole. A normal massive star, say 50 solar masses, ends its life in a core collapse supernova. The core implodes into a neutron star or a stellar mass black hole of perhaps 10 to 50 solar masses, and the outer layers are violently ejected into space. But supermassive stars don't do that. When a supermassive star's nuclear fuel runs out, the entire star collapses. There's no explosion. There's no ejection of material. The entire million solar mass object collapses directly into a black hole of roughly the same mass. This is called direct collapse, and it's one of the leading theories for how supermassive black holes could have formed in the early universe. Here's the problem that astronomers have been grappling with for decades. Observations from the James Webb Space Telescope and other instruments have detected supermassive black holes with masses of hundreds of millions or even billions of solar masses, existing less than 1 billion years after the Big Bang. That shouldn't be possible. Black holes grow by accreting matter, but accretion is a slow process. There's a physical limit, called the Eddington limit, that restricts how fast a black hole can grow. If you feed matter to a black hole too quickly, the radiation pressure from the infalling matter pushes away additional material, choking off the accretion. Even if you assume black holes were growing at the maximum possible rate from the very beginning, starting from seed black holes of a few hundred solar masses left over from the first generation of stars, you can't grow billion solar mass black holes in less than 1 billion years. The math doesn't work, unless the seeds weren't a few hundred solar masses, unless the seeds were a million solar masses. If supermassive stars collapse directly into million solar mass black holes in the first few 100 million years after the Big Bang, those black holes would have had a huge head start. Growing from a million solar masses to a billion solar masses in 700 million years is difficult but mathematically plausible. Little red dots might be the smoking gun, the direct evidence that the early universe was producing million solar mass black hole seeds through supermassive star collapse. Dr. Nandal's team is careful to note that their model doesn't prove this definitively. Models are only as good as the assumptions they're based on. But the fact that supermassive star models match all the observational properties of little red dots is compelling. And there's another piece of evidence that supports this interpretation. The team analyzed the distribution of little red dots across different redshifts, different distances, and therefore different epochs in cosmic history. Little red dots are most common at redshifts between Z-5 and Z-9, corresponding to the universe at ages of roughly 500 million to 1.2 billion years after the Big Bang. At later times, at lower redshifts corresponding to the universe older than about 1.5 billion years, little red dots become much rarer. It's as if something changed in the universe around that time, making supermassive star formation much less likely. That timing makes sense. By about 1 to 1.5 billion years after the Big Bang, the first generations of stars had lived and died, enriching the interstellar medium with heavy elements. Once gas clouds contained even a small fraction of heavy elements, they could cool more efficiently and fragment during collapse. The conditions for forming supermassive stars disappeared. Little red dots might represent a brief window in cosmic history, a few 100 million years, when the universe could produce stars of unimaginable mass. But here's what's truly unsettling about this discovery. If supermassive stars existed in significant numbers in the early universe, they would have had a profound impact on cosmic evolution. Each supermassive star pumps out radiation equivalent to 10 billion normal stars. That radiation heats and ionizes the surrounding gas, preventing it from collapsing into new stars. A single supermassive star could sterilize a region of space thousands of light years across, suppressing star formation in an entire protogalaxy. And when the supermassive star collapses into a million solar mass black hole, that black hole begins accreting gas and growing. As it grows, it launches jets and winds that blow away even more gas, further suppressing star formation. This is called feedback, and it's a critical process in galaxy evolution. Too much feedback, and galaxies can't grow. Too little feedback, and galaxies form stars too quickly and run out of gas. The fact that little red dots existed in significant numbers suggests that supermassive star feedback was an important process in the early universe, one that our models of galaxy formation have largely ignored until now. Dr. Nandal's team is already planning follow-up observations with JWST to study little red dots in more detail. They want to measure the masses more precisely, study the envelope structure, and look for variability that could confirm the supermassive star interpretation. They also want to search for little red dots at even higher redshifts, even earlier times, to see if supermassive stars existed in the very first galaxies, perhaps as early as 200 to 300 million years after the Big Bang. And they want to find little red dots that are in the process of collapsing. If a supermassive star's lifetime is only a few thousand years, and if we're observing objects from billions of years ago, we should statistically expect to catch some of them in the act of dying. What would that look like? Nobody knows for sure. Theoretical models suggest the collapse might be visible as a sudden dimming or as a dramatic change in the spectrum as the envelope is suddenly swallowed by the imploding core. Catching that moment would be the ultimate confirmation that little red dots are what we think they are. But there's another implication that nobody's talking about publicly yet. If supermassive stars with masses of 1 million suns could form in the early universe, what's the upper mass limit? Is 1 million solar masses the maximum? Or could even more massive stars have formed under the right conditions? Some theoretical models suggest that under very specific conditions, extreme gas densities, rapid accretion, minimal angular momentum, stars of up to 10 million solar masses might be possible. Those objects would be even more luminous, even more unstable, and their collapse would produce even more massive black hole seeds. If those objects existed, they'd be incredibly rare and incredibly difficult to detect. But Webb's surveys are ongoing. If they're out there, we might find them. And here's the philosophical implication that makes this discovery so profound. Stars are the fundamental building blocks of the universe. They're the engines that convert primordial hydrogen into all the heavier elements. They're the objects that illuminate galaxies and make cosmic structures visible. Understanding what stars can exist under what conditions is central to understanding cosmic evolution. For decades, we thought we understood the mass range of stars. Observations and theory agreed. Stars could range from about 0.08 solar masses, the minimum mass needed to ignite hydrogen fusion, up to about 300 solar masses, beyond which stars become so unstable they can't hold themselves together. Little red dots shattered that understanding. They showed that under the right conditions, conditions that existed briefly in the early universe, stars of 1 million solar masses were not only possible, but common enough to be detected by Webb. It's a reminder that the universe has regimes and conditions we haven't explored yet. The early universe wasn't just a smaller, denser version of the universe we see today. It was qualitatively different, with physical processes and object classes that no longer exist. Now, let's put it all together. Mysterious red objects scattered across Webb's images of the early universe have been identified as supermassive stars with masses reaching 1 million times the Sun. These stars are metal-free, formed from primordial gas, and surrounded by hot, diffuse envelopes. They shine with the luminosity of 10 billion suns, but only survive for a few thousand years before collapsing directly into million solar mass black holes. And this process may explain how supermassive black holes weighing billions of solar masses appeared less than 1 billion years after the Big Bang. The probability of detecting these objects without Webb's unprecedented infrared sensitivity, without the telescope's ability to probe the early universe in exquisite detail, is 0. We got lucky. We're not saying all little red dots are definitely supermassive stars. Alternative explanations involving obscured black holes or exotic accretion processes can't be completely ruled out yet. But the supermassive star model fits all the data better than any competing theory. We've reached a point where even skeptical astronomers are acknowledging that the early universe was stranger and more extreme than we imagined. The James Webb Space Telescope continues to survey deep space, and more little red dots are being discovered every month. Follow-up observations with Webb's spectroscopic instruments are planned for 2026 and beyond. And here's what this really means. We're witnessing a phase of cosmic evolution that only lasted a few 100 million years. A brief window when the universe could forge stars of unimaginable mass. Those stars shaped the early universe, seeded it with the first supermassive black holes, and then vanished forever as the universe became enriched with heavy elements. Understanding little red dots isn't just about solving a puzzle. It's about understanding how the universe transitioned from its primordial state to the complex, structured cosmos we observe today. So, what do we know for certain? First, little red dots are real objects detected in multiple Webb surveys at redshifts between Z-5 and Z-9, corresponding to the universe at ages of 500 million to 1.2 billion years. Second, their spectroscopic properties, luminosity, emission lines, colors, match theoretical models of metal-free supermassive stars with masses approaching 1 million solar masses. Third, these objects could explain the rapid formation of supermassive black holes in the early universe through direct collapse. What don't we know? What is the exact mass distribution of little red dots? Are they all roughly the same mass? Or is there a range from hundreds of thousands to millions of solar masses? How exactly do they collapse? Do we ever see them in the act of dying? And most importantly, how common were these objects? Did they have a significant impact on the evolution of the first galaxies? And here's the urgency. Little red dots are faint and difficult to study. They require long exposure times with Webb's most sensitive instruments. The James Webb Space Telescope has a finite operational lifetime. Its fuel for maintaining its orbit at the Sun-Earth L2 point will eventually run out, though it's expected to operate through at least the 2030s. Because if follow-up spectroscopic observations in 2026 and beyond confirm the supermassive star interpretation, if we catch variability or find little red dots at even higher redshifts, we'll have confirmed one of the most remarkable discoveries in the history of astronomy. The truth is this: the early universe could produce stars of 1 million solar masses. These monster stars existed for only a few thousand years before collapsing into black holes, and their brief existence may have determined the fate of every galaxy that formed afterward. And the only way to fully understand this process is through continued observations with Webb before our window into the early universe closes. If this video left you questioning everything you thought you knew about the maximum mass of stars, don't forget to click the like button and subscribe to this channel. We're tracking little red dot discoveries in real time as Webb continues its deep surveys, and you won't want to miss what happens when the follow-up spectroscopic observations are completed in 2026. Leave a comment with your theory. Do you think there are even more massive stars hiding in Webb's data that we haven't identified yet? And share this video with anyone who thinks we've already discovered the most extreme objects the universe can produce. After watching this, they'll never think about the limits of stellar mass the same way again. The universe's first stars were monsters.